So as you guys know, my name is Kylie. I'm a physics PhD student at Columbia University, and my research is on the Atlas detector at CERN in Geneva, Switzerland, which is where I've been living for the past 2 years. And so right now, you can see behind me one of the access points to the Large Hadron Collider, which is currently about 100 meters or 300 feet below where the position where I am standing right now. And so, as Mike said, unfortunately, we can't go in there right now, but we did prepare video. But first, I just wanted to add on top of the nice background that you gave of mine, Mike. Basically, I've always really been interested in math and science. And I think ever since I was a young child, and I think my interest in these two fields are kind of come from different parts of myself. So I'm really interested in science because I'm really interested in understanding how things work and trying to figure things out. And I'm really fascinated by math because you can kind of approach problems that you've never seen before and solve them using like this toolbox of mathematical strategies and approaches that you've learned. And so physics is kind of this beautiful marriage between problem solving and being curious about how things work. And so that's kind of where my interest in physics comes from. So you're about to see this really nice video that I helped produce with CERN. So in the video, you'll meet Stephen Goldfarb, who is one of the leading Atlas outreach coordinators here at CERN. And so the two of us do the video together. So you'll meet him as well as myself. And so, yeah, I really hope you guys will appreciate the video. And just a reminder to submit all your questions during the video to the chat box to John Parsons. He will then relay the questions to me after. And so after this, right now I'm kind of right outside where the elevator is kind of, you'll see in the video, like right behind these doors. But after, I'll be answering questions in the actual Atlas control room, which is kind of like right around the corner from here. So yeah, please enjoy the video and I'll see you guys on the other side.
CERN. My name is Stephen Goldfarb and I am a physicist on the Atlas experiment. And this is my colleague, Kylie.
Hi, my name is Kiley Kennedy and I'm a PhD student on the Atlas experiment at Columbia University.
So we're going to be your guides today. We're going to take you on a visit. You're going to get to go not just out here at point 1, the point where particles collide below our feet, but we're actually going to go down underground and see the Atlas experiment. And that's where we collect all the data from the LHC collisions. You want to come with us? Put on your mask. You can't come down unless you got your mask on. We're going to get you a helmet when we get inside, so come along with us. All right, so everybody, we're all going to put our helmets on because we're going to go underground. We're going to be almost 100 meters underground. That's where the Large Hadron Collider collides protons together in our detector. Kylie, lead the way. Kylie's going to head on through our personal access device, or pad, and it's going to check to make sure that she is who she says she is. It's going to check her eyes here with the iris scanner. We're all going to go through. I'm going to go in through next. Okay, everybody ready? You got your helmets on? We're going to push the button and call the elevator up. It's only 2 floors down, but 2 floors down is more than 90 meters. Let me show you where we're going to go. If you take a look over here, you can see what our beautiful little detector looks like. This here, this is wrong. It's 46 meters. I know, I've seen it. It's a long distance from one end to the other. It's a very, very large detector. The whole point is that we surround the collision point. The protons come in here and they collide in the center of that detector. And we produce little people. No, we don't produce little people. These are physicists. That's the actual size of the people who are down there. And so we might see some people now. The LHC is not in operation. Don't worry about that. There are no collisions. We're all working on our detectors. This is a long shutdown. All of the different experiments are working on their detectors, and the people who give us beam, the LHC engineers and scientists, are working to give us better beam with more collisions per second in another year and a half we're going to have that. Okay, let's go down. Take us down. We're going to go all the way down to the bottom. -2. Only 2 floors, like I said, but that first step is a big one.
But if you look right here, you can see this number here shows how many meters below the surface of the ground we are. You can see how rapidly down we're moving to access the detector cavern.
We go underground basically because we couldn't afford the land above ground, right? But the whole accelerator, which is 27 kilometers around, is all buried underground. There are 4 places on the Large Hadron Collider where the protons collide. We surround them with detectors. We're at Atlas, point 1 of the LHC. There are 3 other experiments. If we go around that way, there's the Alice experiment. Other direction, there's CMS, and over there, there's LHCb. They're all very, very important, very beautiful experiments with thousands of people working in collaborations on the experiments. We've made it. We're down at the bottom. One more time, we're going to go through. Kylie, do you want to go
Sure.
first? Okay, we're going to take you inside where you can see the detector. Now here's the thing. You're going to see an enormous device and you're not even going to see the whole of it. You're going to see parts at a time. We have this entire huge device we're going to take you to see, and it's designed to look at the absolute smallest things that exist in our universe. In fact, can't even say large or small, can we? They're fundamental particles that we're looking at, which have no volume at all, right?
That we know of.
That we know.
That we know of.
We will always measure that.
In fact, when we refer to the size of particles, we're not actually referring to the volume that particles take up. We're actually referring to the masses of particles, which we can actually measure more precisely, because of course the volume of particles is something we really don't quite know about. And if we did know the volume of particles, it would unlock a lot of key mysteries.
Well, I think it would then mean that they're not fundamental, probably.
Yeah, it could
right?
be.
Heisenberg, I don't know, says that we're never really going to know, right?
Mm-hmm.
We can never tell exactly when the size is of a particle.
Yeah.
We can't tell its position exactly if we know how much it's moving, and we can't tell how much it's moving if we know its position. It's a strange world, but we're going to take you to see a little bit of that world now. We're at the far end of the experiment. These are called, this is the Muon spectrometer. These are tubes filled with gas and a wire in between. When a charged particle goes through this, it leaves a trace.
It ionizes the gas.
Exactly, it ionizes the gas and sends a charge, which we read out with the electronics. We have to connect the dots to see the track of the particle that goes through. What's really cool here, what I really like, if you take a look here, that's the LHC. See the blue there? If you go underneath that, you're under the LHC.
So the actual tube that the protons go in when they're traveling through the LHC is only about this big. But if you look here, you see what Stephen is touching right now. That huge object is beam shielding that surrounds these tiny proton-proton beams, because as the protons are moving around in a circle, they're accelerating because their direction is changing, and so they emit showers of particles by this kind of circular acceleration. And close to the detectors, we don't want that stray radiation to interfere with the measurements we're trying to obtain from the proton-proton collisions. So we have this massive, massive beam shielding that you can see is probably a couple meters across.
So I mentioned how enormous this device is, and you can see, and you're going to see better when we get upstairs, but I want to show you something that we do here. All these little devices here were made to line up the detector. Now you can see it's fairly precise. This gets us within, say, millimeters here. But we actually line the entire detector up within tens of microns. Tens of microns, the thickness of your hair. And that's over something which is 26 meters in diameter. That's what we have to do to get the precision measurements, to get the most out of the data that we get.
So something I just want to point out, and is something that you'll see throughout the rest of this tour, is how many cables and how many wires we have inside just this room, this cavern. In fact, if you took all of the cables that we have in this room and lined them up from end to end, it would reach to the moon and back with some to spare.
Yeah, we made it. The top of the Atlas experiment at the LHC. I'm so glad that you could make it all the way up here with us. And now, let me answer this one question that you seem to keep asking, is like, why? Why are we doing all this? Why did we build such an enormous device? Why did thousands of people from all over the globe come together to do this? This is no easy task. Why did they all go to their funding agencies and ask for resources to do this? And why do human beings say, yes, absolutely, this is something to do? It's fundamental research. Maybe there are some questions that you could answer or maybe ask that we're trying to seek the answers to here.
Yeah, so I think the fundamental question that us as physicists are interested in is why are we here? Why is the universe the way that it is? And what are we made out of? And so these kind of questions go back all the way to the beginning of the universe, to the origin of the universe, the Big Bang. And so right after the Big Bang, all of the stars in our galaxy and all of the galaxies in the universe were compressed into a tiny volume. And everything, as you can kind of imagine, was super, super dense and super energetic. And so the types of physics interactions and processes were very different back then than they are today. And so we need a specialized system to try to study those early interactions of that very hot and dense universe. And so the way that we've approached this way to study these particles is by simulating, so kind of trying to recreate the conditions of the universe right after the Big Bang. And that's by colliding these protons at these really, really high energies to try to recreate that high energy universe. And so you can see here, if we look down into the detector, you can see kind of through all of these different highly complex layers of the detector is the actual interaction point where we see those two protons come together and collide. And we have a myriad of various layers of the detector that perform different measurements so that when we put it all together, we can identify the kinds of particles and their energies that emerge from these high energy collisions to better study what's actually happening.
Our field really started because we saw that there were these particles we couldn't understand that were kind of messengers from the Big Bang hitting us over the head. There's cosmic particles that come through us all of the time. What we found out from them is that there's a lot more out there than what we're made out of. Ourselves, I don't know about Kiley, but I'm made up of up quarks and down quarks and electrons, and I think she is too. That's what makes up pretty much all of the matter that we know, because those are stable particles. But if you add energy, you can actually create mass, right? E equals mc squared. That's what goes on down here. We take light particles, stable particles, we add a lot of energy, and then in the collisions we can produce more massive particles. The E becomes mc squared. Those particles can then transform to the lighter particles and we get E again. The mc squared goes back to E. We have to reconstruct all that, and we learn about these particles that existed in early time and which can be produced by interactions out in space as well. This tells us about the basic fundamental building blocks of our universe. That's what we care about. Fundamental particles, particles that aren't made up of other particles. We think we have a pretty good model now. We're pretty happy with it. We can put it all on a coffee cup even. We have the particles, and we have on the other side of the coffee cup an equation that explains how they interact. We're kind of happy, except that's about, what, 5% of the universe that we understand. There's a lot of other stuff out there that we're missing. What are we missing? We're missing stuff, right?
So I think we can do a lot of things very well, and I just want to point that out. what we call the standard model of particle physics, which was developed in the 1970s, and which, since its development, piece by piece, particle by particle, we've discovered every single particle predicted by this physics model in the 70s. It's one of the most precise, if not the most precise, model in science that has ever been created by humanity, or that we know of. However, as Steve just pointed out, it only describes 5% of our physical universe. And so we know there is so much more out there that we need to study to really understand the fundamental nature and the fundamental building blocks of our universe. And that's something we're trying to do here. So physicists are looking to study extensions of the standard model. So the standard model, we know it can't be the only be-all and end-all physics model. So people are looking to add particles to the standard model to explain various kind of questionable phenomena that we have observed so far. One of those being dark matter. So dark matter is about 20 to 25% of our universe, and astronomers and astrophysicists have measured this, except we don't yet know what particle or set of particles is responsible for our observations of dark matter, and we have good reason to think it is indeed a physical form of matter. And so that's one of many things that we are trying to create here at the LHC in conjunction with thousands of other scientists and other collaborations and theorists and phenomenologists who also are interested in studying dark matter. And that's just one topic of many.
Then the other dark thing that we're missing, it's great because our great-grandchildren are going to laugh at the fact that we call these things dark just because we didn't know what they are. But that's why science is so fascinating. We're looking for stuff we don't understand yet. The other thing that's dark, we call dark energy, and that's most of the universe, right? That's whatever energy is out there that's making us expand faster and faster. The universe itself is growing and going at a faster and faster rate. We don't get that, and a lot of people don't get that. It's not clear particle physics will answer that. Could take other forms of physics. Could be astronomy will give us some answers, astrophysics, we don't know. But we have a lot of big questions, and we're going to try to answer them. And that's why we're continuing. We're upgrading this. We're upgrading the LHC. We're going to do that again later on. It's all planned. And then we're going to look to do something even higher energy, because that's what we have to do. We're human beings. We're curious. We got to find the answers. Maybe now we should go back down halfway and take a look where you can get a little better view of the detector itself. You guys ready for that? You're not too winded, are you? Come on, let's go on down. Now you have a view you might be able to comprehend a little better here. So what do you think of that, huh? So let me explain a little bit here. What you can see from here on is what we call the barrel part of our detector. So that's the central part. The beam comes in all the way through and collides in the center of the barrel there. That's one of our enormous magnets. We have a couple magnet systems at the ends of the detector. So we surround our detectors with these very powerful magnets. These big tubes here are magnets as well, and that curves the particles. So when a particle is curved by the magnetic field, we can then look at how much it gets curved and figure out what its energy is, or what its momentum is what the term that we use. And you know that because the more it turns, the lower its momentum was.
There are a variety of different layers of the detector that do different measurements. And so when you have the two proton-proton beams coming and colliding, the first layer of the detector is what we call the inner tracker. And we have a specialized system which tracks the paths of charged particles that, as Stephen said, are in the presence of a magnetic field. And so we can track the bend of these charged particles very precisely. And then after we have this tracker, we have our calorimeter system. And so our calorimeters measure the energies of the particles produced in the detector, and they do that by stopping the particles and forcing the particles to deposit all of their energy into the calorimeter so that we can measure it. And that's part of the reason, another reason why we need such a big detector is because these particles produced in the collisions are so energetic that we need a thick material and a dense material to actually be able to stop particles that energetic. And so we have a couple different types of calorimeters that measure the energies of different kinds of particles. And then on the outside, we have our Muon spectrometer and our magnet system, which Stephen has pointed out to you already. And the Muon system is specially designed to measure these kind of funny particles called muons, which are considered the heavier cousin of the electron. They have almost the exact same properties as electrons. So as you know, typical electrons just orbiting your standard atoms that we see in day-to-day life, except the muons are heavier. And so because muons are heavier, they kind of fly through the inner part of the detector, and we can't capture them in our calorimeters. And so we have this specially designed muon spectrometer to actually be able to measure these muons, which are really important to our understanding of new physics.
These little targets here, we have targets on the detector because we actually take images with cameras to see how far the detectors move. They move over time because they're so large. And so you got to keep track of that in order to line everything up with the software down to the tens of microns of precision that we need.
See all in here, all of the rich
I've been down
detail.
there. I've been down there.
I know, all the cables.
One of the really cool things we get to do is when the shutdown is over and we're getting ready to come back on, then all of the collaboration comes, well, not all the collaboration, but whoever's around comes here, gets down on our hands and knees, we put on gloves, and we pick up anything and everything, because when you have a strong magnetic field, if there's a little screw that's on the ground that we forgot, it can shoot out like a bullet. So we have to clean everything up. Your head out over there and take a look, and you're going to see part of our detector. That's the small wheel that's sitting out in the middle there. We're working day and night to be able to replace that with, okay, catch this name, the new small wheel. We're working on those for many years now. It's a very important upgrade.
What we're doing right now is a trigger upgrade, and I'll explain what a trigger is. So in the Atlas detector, we see 40 million proton-proton collisions per second. However, unfortunately, we can't write all of those to disk. We can't save all of those proton-proton collisions. In fact, we can only save about 1,000 per second of the 40 million. And the reason why, some people ask, you know, why do we even have 40 million per second when we only write 1,000? And that's because not every collision is created equal. It's incredibly difficult to actually collide two objects as tiny as protons. And so sometimes we get what we call hard interactions, which is when the protons really collide head on. And then sometimes you produce glancing interactions. And so the collisions that have these hard head-on interactions, those are the ones that are likely to produce collisions that we're really interested in, that we want to keep to study. And so we have a very elaborate method of determining very, very quickly, do we keep this event or do we not keep this event? And so right now we're improving, we're doing a number of different hardware upgrades on all of these different detecting subsystems to improve the quality of our trigger so that we're not accidentally throwing out events that we might actually be interested in. And so some of you may know the last elementary particle we discovered here at CERN and the LHC was the Higgs boson in 2012. And so now in 2020, it's been 8 years and we haven't found anything else. And so some people are wondering, you know, maybe we're accidentally throwing those events away, and so without even knowing it. And so this trigger upgrade is really important because it might help us keep the events that have this new physics that might help us discover a new particle or new interaction or new physical phenomena.
Yeah, that's a really good point. Now, just to be clear, we haven't found any other fundamental particles.
Yes, elementary, yeah.
Exactly.
Elementary.
But we have, there's been a lot of amazing things going on. not just at Atlas. Atlas, we've seen some really cool things you would never believe, like light scattering off of light. Okay? It's a really, really rare phenomenon, but it can happen. It's predicted, and we see that. We can produce things, even not just light scattering, but light hitting each other and producing matter. And that's really an incredible thing to see.
So if you look up, you can almost, maybe you can see the surface. So we have this tunnel, this opening, and that's where we raise and lower equipment to build this detector. And so, you know, our detector is much bigger than the opening above, and so it was kind of built like a ship in a bottle, you know, bringing small pieces down and constructing them down below the surface in this cavern. So right now we're entering the service cavern next to the detector. And so we're not actually in the detector cavern right now. We're in a cavern slightly adjacent to it. The detector is actually kind of through that wall down there. And part of the reason why we have this cavern here is because this is accessible to people while we're taking data, while we have proton-proton beams in the next room in the detector. Because normally when we're taking data, no one can go into the detector when we have these proton-proton collisions because of the extremely high radiation levels. They're not safe for humans. And so we put a lot of machinery that we need to collect data from our detector in this room so that in case something breaks or in case we need to modify something, people can come down here. You know, we're a little less than 100 meters underground. People can come down here and work with the machinery. So I just want to give you a little sense of the extent of all of the computational resources we're working with. It might be a little loud in there, but I'll just give you a bit of a walk around. So we have all of these racks of computers, and these are responsible for everything from high voltage control to triggering to actual data taking, and the computers we use to control the detector, to monitor the detector to make sure that you know, it's responsive and it's doing what we want to do. And again, you can see here we have all of these cables. A lot of these cables actually end up in the detector itself. And so I just want to show you all of these thick black cables here and then all the way down here. This is our current, this is the system that's currently responsible for our trigger. And so all of this is analog. And so all of these wires are coming out of the detector and are the first system to read any information from the proton-proton collisions. And so because all of this is analog, this is part of the system that we're currently upgrading to create a digital trigger that it will do a better job of discriminating between the collisions that we want to keep and the collisions that we might want to throw away. I just want to give you a sense of kind of the vastness of all of these signals that are coming out of the detector that you can actually see in virtually at least. And so even though we're doing an upgrade and the detector is constantly being modified with new hardware, that doesn't mean the detector is off. And so things are constantly running. People are making sure that as we add things, the detector is continually working. It's not like we turn it off and 2 years later we cross our fingers and hope it works. And so this level and the level below all contains these systems, these computers that help us do what we need to do. And then of course we have many more computers upstairs, and then a number of mass computing resources provided by CERN that we can't even see, don't even have time to see today.
everyone. I hope you guys enjoyed the video. And so the last time I left off in the video, as I mentioned, I was around 100 meters below the surface, kind of essentially right below where I am now. And right now I'm currently standing in our control room for the detector. And so I'll just give you guys a few seconds to kind of look over this entire room. You can probably see, hopefully, all of these different computers and seats that are constant, that normally during data taking, when we're actually collecting data, a lot of these are filled with people like myself, monitoring the detector, making sure it's working. And we're very close to the actual access point. It's just right around the corner, as I mentioned before, so that in case you're in here and you need to go down into the service cavern next to the detector to fix something or to check something, you're very, very close. And so normally during data taking, when it's very, very quiet and everything is running smoothly and there are no problems, which is how we usually like it, there are usually at least 8 to 10 people in this room. We have a safety officer that kind of sits over here in the middle. And then we have what we call shifters, who are responsible for monitoring each detecting subsystem and just making sure that nothing is breaking, that the data is being read out correctly. And we're constantly communicating with each other to make sure that the systems are all up and running and that everyone is kind of doing the various tests that they need to do. And so that all happens within this room. When I was a shifter, I sat kind of right over here at this LAR stands for liquid argon, which is the liquid argon calorimeter is one of our calorimeter systems. So that's where I've done a lot of my work. And so I would sit there for these 8-hour shifts. But I'm really excited to hear all the questions that you have. So I'm gonna now hear from John, who's been collecting all of your great questions.
Okay, Kiley, thanks very much for this really fascinating and very well narrated tour and view inside the Atlas detector. So yeah, we've gotten a bunch of questions. So why don't we just jump straight in? So people are interested in so you mentioned you were living in Geneva now, and people are wondering just a little bit about what that's like now in COVID times, at conditions there, and at CERN. How are things operating, and how are you managing?
Yeah, so overall, it's things are pretty good. I'm still able to come to CERN if I need to, but that said, everything that we do is available to do virtually. Not most things, maybe not everything. You can't physically work on the detector remotely. You have to be there. But actually, one of the really nice things that made it easier for, I think, a lot of people who work on the Atlas experiment to transition into COVID is because we're such an international collaboration from hundreds of institutions from the US, Europe, Africa, Asia, South America. We already kind of have this infrastructure and culture of having things available virtually. And so that transition was not as difficult as I think it was for many other people who weren't used to it. In terms of how things are in Geneva right now, we've had some pretty strict restrictions the past month, but things are starting to open up in advance of Christmas. So things are going well. People are still coming to CERN, going to the restaurant, albeit there are very strong social distancing guidelines. But yeah.
Okay, great. And you mentioned the international aspect. So maybe you could say a little bit more about that. So in terms of the Atlas collaboration, sort of, how many people, how big is it, how international, and what's it like, on a daily basis to work? How do all these people work together, and what's that experience like?
Yeah. So there's around 3,000 to 5,000 people who work on Atlas. It depends how you count the numbers. There's around 3,000 authors on the authors list. So basically every paper that gets published by Atlas has everyone on the authors list. But you have to earn your way onto the authors list. And so when I first started out doing research as a summer student, and even in the beginning of my graduate studies, I was not an author. but I am now an author because I've contributed a substantial amount of work to the continuing of the detector operations and detector upgrades. And so the 3,000 number counts people like Professor Parsons, myself, postdocs who were students, or all of the many, many engineers that we really rely on to make everything come together. In terms of what it's like to work here with a lot of other people. So even though I'm part of the Columbia Atlas group, I work with people from all over the world from other universities. And the way that works is essentially because we're all collaborators on the same experiment, you can be working very closely with people from these other institutions. So for example, when I was working on detector operations for the liquid argon calorimeter, we would have multiple meetings per week, sometimes every day, with people from Europe, from Asia, from the US, and we were all kind of, working next to each other, helping each other out in that sort of way. And now I'm currently focused on an analysis where we have multiple institutions chipping in, where you're constantly, collaborating with people from other universities and other countries even. And I think that's actually one of the coolest places to be. That's one of the coolest things about being here, is just like being around really incredibly smart and talented and interesting people from all over the world. And I really appreciate, I've had a very fortunate experience where I feel like I've been very supported by all of these people. So yeah.
Very good. And a follow-up question. So someone asked, so what language how do all these people talk to each other?
So the predominant language of Atlas is English. However, CERN, so basically Atlas is an independent organization from CERN, but we're located at CERN and we use a lot of the CERN resources. We're in the CERN buildings. And so we're on the CERN email server. And so there are two official languages of CERN, which are both French and English. And so typically when we're communicating about physics, we speak in English. However, if I need to go get my dosimeter, which is the device which measures your radiation levels, which I was wearing in the tour, it was kind of the blue thing around my neck. So when I go get my dosimeter, those are CERN staff, so I'll usually speak to them in French because they're French and it's their native language. And so so a lot of the times when you're dealing with, you kind of communicate in both. I know people who also communicate in French a lot more frequently. So it's kind of a mixed bag, but mostly French and English.
Okay, great. Let's turn to the science. So there are questions related to, how the experiment works. So you talked about 40 million collisions per second, but people sometimes talk about 1 billion collisions per second. So could you explain that a little bit? And in terms of the actual operation, so how does it work when data taking is underway? Do you do dedicated experiments, or how, what's the operational mode?
Yeah, so I'll answer that second question first. So our experiment is not like maybe say a telescope that's orbiting the Earth, where astronomers will apply for time on the telescope and then conduct their experiments. On Atlas, we can use all of the data that's collected. It's not like Columbia gets the data that's collected in June and then another university gets the data in July. We're all able to use all the data once you're on the experiment. You don't even have to be an author to use all the data, as long as you're part of the collaboration. But everyone chooses to use it in a different way. And so if your particular physics analysis is really interested in electrons, then you're going to look at all of the data and you're going to only select collisions that resulted in the production of an electron. But if you're really interested in an analysis that has a quark in it, then you're going to go through all the data and only use the data that maybe has a quark. This is, of course, a little bit simplified, but everyone uses all of the data, but in slightly different ways. And so, yeah. So then your previous question was, okay, so in terms of, how we collect the data. So so normally when we're collecting the data, it's running 24/7. So 24 hours a day, 7 days a week, typically from April into November or December of the year. And so, when we're here in this, in the control room, there's people who are here from, 11 p.m. to 7 a.m. doing these midnight shifts. We're constantly collecting the data. And the reason why we don't operate in the winter is kind of twofold. So one, because Geneva is a very cold place in the winter, the operational costs of the LHC are much higher in the winter than they are in the summer. So that's kind of one thing. And then the other thing is that it kind of breaking up data taking and not taking data from like December to the beginning of April allows you to kind of go into the detector and tinker with things a little bit in case you need to. Now, of course, right now we're not taking data for a period of over 2 years, and that's because we're doing a major upgrade. And so we don't have enough time to do everything that we need to do in a period of a few months. And so we kind of so all of the experiments on the LHC, including the LHC itself, are all doing these kind of independent, but also coordinated efforts to upgrade their systems right now. And then we'll start taking data in 2022, and hopefully we'll all be ready for that. In terms of how the proton-proton collisions happen and why I said 40 million, but sometimes you hear a billion, is because the way we produce the proton is because of the way we produce the proton beams. So protons start off as hydrogen, which is essentially just a proton with an electron orbiting it. And we're able to strip the electrons from this hydrogen gas so that we only end up with hydrogen ions, which chemists call it hydrogen ions, physicists call it protons. These are the same thing. And so then we're able to accelerate these now protons, and we don't actually have, basically we don't actually have like individual protons coming in and colliding with each other. We actually have proton bunches. So we have billions or maybe even trillions of protons in a bunch, and billions or trillions of protons in another bunch. And then we have the bunches cross each other. And so even then, it's so difficult to get protons to collide, even though you have like billions and billions coming together. But on the off chance that you do, so basically we're interested in the collisions where we, on the off chance, have these protons collide very head on. But you get a lot of collisions where you might have like a glancing interaction that I kind of tried to describe in the video. So we do get multiple collisions, up to like 100 or so, 30, 100 to 100 collisions per bunch crossing. But there's 40 million bunch crossings per second. But then with each bunch crossing, you get multiple collisions. But we're really primarily usually interested in one of those collisions, which is like the hard head-on collision, which is very rare, which usually only happens once in a bunch crossing. So that's kind of why people throw around this 40 million, because it's 40 million bunch crossings per second, whereas you do get kind of closer to a billion collisions per second.
Great, thank you. Now, so let me combine a couple questions relating to you talked in the video about the early universe. So how is it that we know the universe is expanding is one question, and also how do you know that the things you would make in these collisions at the LHC are the same things as from the early universe, and how can you learn about the universe today from studying things from those early moments after the universe? So it's sort of a big question connecting the research you're doing to the early universe and the evolution and how we can try to learn about it.
So the first question about how we know the universe is expanding. So this is less what we do, but it's what our colleagues in other areas of physics and astronomy do. So you can basically, we know how basically astronomers can point their telescopes in kind of the farthest reaches of space, and you can see what we call red shifting and blue shifting. And so basically, if you have an object moving towards you, let's say even an ambulance moving towards you, you'll notice the sound of the ambulance changes when it passes you. And that's because as it's coming towards you, the sound is being scrunched. And as it's moving away from you, the sound waves are being kind of expanded. And so we observe the same phenomena as we do as an ambulance passes us, but with light from the very distant stars and galaxies of the universe. And so astronomers can point their telescopes and measure these wavelengths of the light that we observe very, very precisely. And they're able to see essentially redshifted galaxies all around us, no matter what direction, if they look this way, if they look this way, if they look this way. And so that led essentially to the theory that the universe is expanding. And so yeah. In terms of the second question, so how we know we are recreating the particles from right after the Big Bang. So I guess, I mean, the answer is that we don't know. So we're trying to do our best. And so what we do know about the Big Bang is that right after the universe was very, very hot and dense and energetic. And so we're not trying to recreate the Big Bang. And however, we're trying to kind of recreate the conditions of the Big Bang. And this is how we've essentially how we're essentially approaching this problem. So we're not 100% sure if we like produce some particle in our proton-proton collisions. We can't 100% with 100% certainty say this particle is kind of the same type of particle that was produced right after the Big Bang, but we can have reason to believe that this particle plays an important role in our universe. So part of the reason why we are interested in searching for all these new particles is because, I mean, I think I don't really know how to like give an explanation other than I think it's really, really cool. I think it can have very far-reaching applications in the future that we can't really understand. So for example, like when the electron was discovered, people kind of said, so what? We don't really care about the electron. But now, of course, the electron governs our life, governs all of our electronics. It is a very important particle, as we know. And so in terms of what we might discover with these new potential particles, we don't quite know. But I think, CERN's basically, CERN was founded on the principle of science for the sake of science. And so if we can search for these kinds of things, why not?
And what I don't know, discovery or thing coming up are you most excited about personally in the science realm?
So my current thesis analysis is a supersymmetry search. And so supersymmetry is what we call an extension to the standard model. So we know that the standard model and all the particles and interactions exist, but we know it's not the complete picture. And so one way that there's also a lot of problems with the standard model, kind of these like mysteries. Like, for example, why does a certain particle have the particular charge and mass that it has? And so these are kind of these like open questions. And so supersymmetry is kind of an extension on the standard model, and it's very elegant in terms of the mathematicians will tell you when you write out the equation, everything is beautiful. And when supersymmetry also is compatible with string theory and also provides a good dark matter candidate. And so supersymmetry can solve a lot of things. I don't necessarily think it's 100% the thing, but my thesis is on a supersymmetry search. And so I would be very excited if my thesis, I see John smiling, I would be very excited if we actually found supersymmetry, whether it would be for my thesis or not. So I think something with supersymmetry or dark matter would be probably the most exciting finding we would, fingers crossed, make. But yeah.
Sounds good. We look forward to that discovery, hopefully. Let's see, so there's a question related to something what you just said, which, you know, a few people are asking. So it's nice that it's cool. You know, what do you see as potential applications in society and future life? How will this impact people's lives? This sort of work.
Yeah. So something that CERN is quite famous for in the 1980s was the development of a system that would be able to connect all of the collaborating scientists to be able to communicate with each other and collaborate better on science. And what was developed was the World Wide Web, which is basically the skeleton of what we now know as the internet. And so I think in terms of like the long-term implications, I think it can be as far-reaching as the internet. As I mentioned with the example with the electron, we really can't, a lot of the innovations that I think we'll create here, we can't really imagine. In terms of the practical applications, we're by running these experiments, by running the LHC and the Atlas detector and the other detectors, we have to solve these very particular problems under these very harsh constraints. And so by kind of so basically we need to solve these problems that no one else has ever done before, these practical problems, like how do we do this particular measurement? How do we measure the energy of this electron and then translate that into the numerical value that you get when you're programming for an analysis? So I think a lot of these systems are like custom designed by us physicists collaborating with engineers. And so a lot of these computer chips and electronics boards and technologies are being developed here for this particular experiment that can then be extended to other areas of technology in the world.
Very good, thank you. Let's see, so I'm receiving lots of flattering comments about how great you explain things. So that's very nice, you should know. I'll pass them on to you later. So there's a question very much in that line, which is for the kids on this call watching, thinking maybe they'd like to grow up to be like you, what advice would you give them? How do they get involved? What should they be doing? So again, it comes back a little bit to, you know, what your life path was that got you here. How, you know, what advice would you like to communicate to those kids watching now?
So I would say, so first I have to say hi, Gabriella, because I know this is my goddaughter who's watching, very exciting. So I would just say, stay curious and stay creative. I remember when I was really little, kind of like opening up these science books we would have in my house, and I wouldn't even know what was going on in the images, but I was just kind of fascinated by all of the diagrams. And I think people, so kind of keep doing that, keep asking questions. And one thing I want to stress is people really underestimate the connection between art and science. I think people think of sciences as like, you need to be very logical, and art is like, you know, you need to be creative and open your mind. But I actually think that science is really an area where you need to be creative and open your mind, because you don't make scientific discoveries by just following the theory or following what you learned in your class. So really just, you know, keep asking questions, keep asking why, keep being curious, and really just do what you're interested in, what you're passionate about. Maybe you realize that you want to be one thing, but you realize that later down the line, you love something else. Just follow that and yeah, stay curious.